There's a lot that you can discover about a function just looking at the equation and not having to graph it or do any specific algebra for it. So Roman numeral 1, first thing that you can notice about a function is it odd? Is it an odd function or is it an even function? Okay, so right down the middle of those two words, you can put a line all the way to the bottom of the page. Okay, so for an odd function, what we're referring to is the highest power of x. So the highest power of x is usually referred to as the degree of the function. And so if the degree is 3, 5, 7, or 1, then it's considered an odd function. If your degree of your function is even, so we're talking 2, 4, 6, 8, things like that, then it is an even function. Okay, so let me give you an example of an odd function. Y equals 2x cubed. That is definitely an odd function. And then something like negative 2x to the 5th plus x cubed is another type of odd function. And again, you know it's an odd function because the highest power on the x is actually an odd number. When you graph an odd function, the basic shape of your graph, we just kind of say it's an S shape. Okay, and then draw yourself a pair of axes about the size of a Post-it. So an S-shaped function starts, it might have some extra bumps in it, but it kind of forms sort of an S shape, either going up or going down. It can be completely smooth as well. But if your function is going up, then that function will have a positive a value. Now your a value is the number attached to the highest power of x. So on our examples for 2x cubed, my a is the 2 attached to the cubed x. For the other one, my a is the negative 2. So when we're talking about an a value, it's that coefficient, the leading coefficient. So you have going up and you have going down, which would be, of course, a negative a in the function. So the first example I gave you with the positive 2 would be going upwards. It might have some bumps in it. The second one with the negative a is the one going downward. And again, it might have bumps. It might be smooth. Okay, so using the odd function, we can talk about end behavior. End behavior. And for the sake of clarity, I'm going to number that curve 1 and that curve 2. So your end behavior for curve 1, we say as x approaches positive infinity. That means as x goes to the right, y approaches positive infinity, the y value goes up. So you can see on this function, as I go to the right, the y value is shooting up. As x goes to negative infinity, as I go to the left, y also goes to negative infinity. So as I'm going to the left, this function is going downward. So the y's are getting smaller. So that's if you have an S shape going up. Now our second curve is an S shape going down. So in this case, as x goes to positive infinity, which is to the right, your function is dropping. Y goes to negative infinity. As you go to the left, so as x approaches negative infinity, so as you go to the left, this going down curve actually is shooting upward. So y approaches positive infinity. And that's how you describe the end behavior of the curve. The first half is always the same. As x goes to positive infinity, as x goes to negative infinity. What changes is what is the curve actually doing as that's happening. Okay, so that is an odd curve and what it looks like. Okay, so now we're going to go back up to the top. And we're going to do the even curve. So an even curve, some examples of even curves would be y equals 2x to the fourth. That's an even curve. Or y equals negative 3x to the sixth plus x to the fifth. So again, the highest power on x is the degree. And in this case, that highest power is even. So the shape of this, and it's hard to describe shapes using words. So we sometimes call this a camel graph because it has legs. So draw yourself a pair of axes. In camel graphs, you either have legs up, dead camel, or you have legs down, live camel. So if your A value is positive, then you've got dead camel. If your A is negative, you have live camel, legs down. So in the equation examples that I gave you, the A value for the first one is a positive 2. So that would be legs up, dead camel. On the second equation, the A value is the negative 3, which is attached to the x to the sixth. And that would be live camel, legs down. Okay, so let's get into the end behavior, which is the official way to describe what the graph is doing. So again, for the sake of clarity, I'm going to number the first graph 1 and the second graph 2. So for number 1, which is dead camel, legs up, as x approaches positive infinity, as x goes to the right, your y values are shooting up. So y approaches positive infinity. As x approaches negative infinity, so as we go to the left, y is still going up. So y approaches positive infinity, regardless of whether you're going to the right or to the left. Now, on the second graph, it's the exact opposite. In this case, it doesn't matter if you're going right or left, the y values are dropping. It's legs down. So as x approaches positive infinity, y approaches negative infinity. Y approaches negative infinity. Let me fix that. Here we go. And as x approaches negative infinity, as we go to the left, y still is going down. Y approaches negative infinity. So legs up, everything's going to positive infinity. Legs down, everything's going to negative infinity. Okay, so let's do an example using what we just learned. Okay, let's say f of x equals 3x squared plus 1. And when you have it in standard form order, the degree is typically based on the first term. So in my very first term, it's an x to the power of 2. So this is a degree 2 function. 2 is even. So we have a camel graph. All right. The leading coefficient, which is your A value, is the number attached, which is a positive 3. Again, the 3 is positive, which means legs are up or dead camel. So if I had to sketch without really like running points or anything specific about this graph. It's going to be a camel graph, legs up. It probably crosses somewhere, we're not sure, but that's your basic shape of the graph. All right, let's do one more and then we're going to move on to the next topic. So let's say you've got f of x equals x cubed minus 1. Okay, in this one, the highest value of x is a 3. So your degree is a 3, which is an odd number, which means we're going to have an S-shaped graph. Okay, now we're going to look at the leading coefficient, or the A value. The A value is the invisible 1 on that x cubed term. So it's 1, which is positive, which means it's going to be an S going up. So again, draw yourself a pair of axes. If you wanted to sketch roughly what this would look like, it's an S shape going up. So it's probably got some bumps in it and then it heads upward, S shape going up. All right, so that's how you use the degree and the leading coefficient to get an overall shape. All right, so Roman numeral 2, we're going to go to the next classification topic. So Roman numeral 2, zeros and multiplicity. Zeros and multiplicity. We're going to start with zeros. Okay, to find the zeros of a function, first thing you need to understand that zeros are the x-intercepts. They get their name because at an x-intercept, y equals 0, and that's why they're called zeros. So what you need to understand about zeros is that every factor has a 0. And it might have more than one. It's possible to have 1, 2, 3, and so on, depending on the type of factor you're looking at. So to find a 0, you set all factors equal to 0 and solve. So here's an example. Y equals x times x minus 1 times x plus 2. This is a factored form. In order to get zeros, you have to do factored form. So to find the zeros, we change y to a 0, and we're finding the zeros, or the x-intercepts. So you're going to take each factor and set it equal to 0. So set x equal to 0, set x minus 1 equal to 0, set x plus 2 equal to 0, and solve. So we get x equals 0, x equals 1, x equals -2. And those are your zeros, or your x-intercepts. It's where your graph crosses the x-axis. Okay, that's zeros. Okay, B, we're going to do multiplicity. Okay, multiplicity refers to how many times the same factor appears. So identical factors, how many times? And there you can break them into odd and even. So if there is an odd number of a factor, the graph crosses at that point. If there is an odd number of a factor, the graph crosses at that point. Okay, so the next rule, if there is an even number of a factor, the graph touches, or sometimes we say it kisses, the x-axis at that point. And a really easy way to remember is it takes 2 to kiss. So if there's 2, 4, 6, 8, then it's going to touch the x-axis and head back the other way. So yeah, that's our memory handle. It takes 2 to kiss. If you can remember that, you'll keep the rules straight. All right, so let's do an example. Let's say you've factored this guy, and it is x plus 2 cubed, x minus 1 squared, x plus 4, x, and x squared. Okay, so the number of factors tells you if it's going to kiss or cross. So for the first one, it's to the power of 3. That's odd. So this one's going to cross. The next one is to the power of 2. So there's 2 of them. That's even. So that's going to kiss. It's going to touch at that point and turn back around. X plus 4, there's only 1 of them. So it's going to cross. Now, with single x's, you do have to simplify them together. So x times x times x is x cubed, which is odd. So it's going to cross. Now, the question is, where is it going to cross or kiss? Okay, if you set each factor equal to 0, your x plus 2 is going to cross at x equals negative 2. It's going to kiss at x equals 1. It's going to cross at x equals negative 4. And for the x's, it's going to cross at x equals 0. And that's something we've been practicing, is how to solve from factors. All right, we're going to pull all this together. We're going to pull together type of graph and end behavior, zeros and multiplicity. I'm going to use a page for this, so I'm going to turn the page and get a fresh page. All right, example. Let's say you have f of x equals x plus 1 squared times x minus 3 times 2x plus 4. And your mission is to sketch a graph. This is different than plotting a graph. Sketching a graph means you use the rules to do it. Okay, so the first thing you need to do is figure out the degree of the polynomial. So if you were to imagine that you were going to multiply all these factors back together, which we're not going to do, your x plus 1 squared would have an x squared as its first factor. For x plus 3, it would just be a single x. And then you have a 2x plus 4, you'd have a 2x, because that's the first term. And if you multiply those together, you end up with 2x to the 4th as your first term. So to figure out what the first term is, basically you just multiply together with the powers the first terms. Okay, so the degree of this, so this is a degree 4, which is even, which means it is a camel graph. The leading coefficient, or the A, is a 2, which is positive, so it's a camel graph legs up. All right, if I had to list the end behavior, remember we're thinking camel graph legs up. So end behavior always starts out as x approaches positive infinity and and x approaches negative infinity, excuse me. The left-hand side is always x going to the right, x going to the left. And then you just say what the y's are doing in each case. So looking at my little mini sketch, as x goes to the right, as x goes to positive infinity, the y's are shooting up. So y approaches positive infinity. Looking at the little sketch, as the x goes to negative infinity, as it goes left, the y's are also shooting up to positive infinity. So that would be your end behavior. Okay, now let's do the zeros. We're going to set each of the three factors equal to 0 and solve. So I'm going to set x plus 1 equal to 0, x minus 3 equal to 0, and 2x plus 4 equal to 0. And I know you know how to solve that, so I'm not going to go through that. We're just going to list what you get. You get x is -1, x equals 3, x equals -2. So those are the zeros. Now we're going to list their multiplicity and what that means. Okay, so going back to the function, the x plus 1 factor appears twice. So the multiplicity is 2. Takes 2 to kiss. This is a graph kiss. It's going to touch and go back the other way. X minus 3 is only one of those. That's odd. So that's going to cross at 3. And 2x plus 4 only occurs once. That's its multiplicity, which means the graph will cross at -2. Okay, so now we're going to pull this together and do a graph sketch. So draw yourself a pair of axes. And what I usually do is mark my zeros out before I start. So x, and I'm going to space these out a little bit. So x is -1, that's a 0. -2 is a 0. And then 1, 2, 3 is a 0. So every 0 represents a place where the graph either kisses or crosses. So you can put an intercept at each of the 3 zeros. I have 3 intercepts. There they are. Now, we already established that this was a camel graph, legs up. So the farthest 0 to the left is going to shoot to positive infinity. The farthest 0 to the right is going to shoot to positive infinity. So now we're going to obey the rules of multiplicity. At -2, it's a cross. So we're going to cross and go back up to the -1. At -1, it's going to kiss. So it touches at -1 and it turns around and goes the other way. And then at +3, it's going to cross. Your multiplicity and your type of graph should go together. So if these 3 things don't agree with a camel graph legs up, then something's wrong. Either it's not a camel graph legs up or you got your multiplicity mixed up. But that's a pretty good graph just looking at the equation and not seeing anything else. Okay, any questions about any part of this project?